This is very similar to the magnetic field sensors that we used in lab the other day. So what we've got, you may have wondered how those sensors worked, measuring those magnetic fields, right? They work on this almost the exact same principle. We've got a strip of metal, and we know the dimension there. Call it W or D, or we know the dimension of this strip of metal, and we've got a current flowing through here, and this is in a magnetic field. So we've got a region here. We put this probe into a magnetic field. What direction? Into the page, out of the, let's go into the page. And then what we do, we measure the voltage because where the positive charges end up? At the top, where the negatives? We measure the voltage. If we knew the width of that metal strip, the same thing happens, right? At some point, the charges stop moving. We reach an equilibrium state. The potential becomes constant. And if we measure the potential and the width, and we know the velocity of those particles, which we can get as the drift speed of the particles, of the electrons, then we can figure out what the magnetic field is. That's called the Hall effect. Probe, that's what the Hall effect does. We can use it to measure the magnetic field. But something interesting, there's something interesting about this Hall effect. I told you that we can view, right, we were stuck with this convention that current is the direction of positive charge flow. And really, negative charges are moving in the opposite direction. Okay? And we've said that they're equivalent. But what I want you to do is write out what would happen. Let's draw the picture here. If positive charges move, and then also draw it if negative charges move. And what happens in the Hall effect? Do we get the same result? So here's our strip of metal. Our current is going to the right, which means that's the same over here, right? Doesn't matter. So if positive charges move, that means that positive charges are moving this way with some velocity v. That's what a current to the right means. If negative charges move, it means that a negative charge is going to the left. That's what a current to the right means, right? These are I told you up until this point we've said these were equivalent. A current to the right could be a positive charge moving to the right or a negative charge moving to the left. How do we know which one is moving? Have we talked about that? Ah, okay. There's a couple of interesting experiments. This is actually the third way we can tell which charges move. So we're in a magnetic field. What happens to that positive charge moving to the right with the magnetic field into the board? We just did it, right? Goes up. Right, we get that. What happens with the negative charge moving to the left in that magnetic field? Where does our negative charge go? Up. So in this case, it's not the same. We can measure the potential difference here and see which one is at higher potential with respect to the other one. It turns out this is what's actually happening. The negatives are moving, not the positives in our metal strip there. That's a metal strip, a conductive strip. The negatives are moving, the electrons are moving. How else do we know which one's moving? There's another, maybe you did this experiment when you were a kid. You had your wagon. You had a ball in the wagon. You pull the wagon. What happens to the ball? Yeah, actually, it wants to stay where it is, right? Because it has inertia. And the wagon moves forward, and the ball wants to... Oops, that's not very straight. The ball wants to stay where it is. The wagon moves forward. This is if we accelerate it, right? And then it moves along. And if we stop the wagon, the ball wants to keep going, right? It's inertia. So the idea is, let's take a conductive material. We know that in a conductor, something is free to move around. It's either a positive charge or a negative charge. Something in there is free to move around. So if we accelerate it to the right, whatever it is that's free to move around, that causes whatever charge that moves in there is free to move around, what's going to happen to it? It's got inertia. Those are particles with mass, right? Electrons have mass. Positive charges have mass. Protons have mass. They have inertia. They don't want to move. They don't want to accelerate. They're going to resist that. So whatever is free to move is going to bunch up at the back of the wagon, right? So if we take this metal, this conductor, and we accelerate it, right, one of two things can happen. If positives If the positive charges are free to move around, they're going to bunch up at the back of the, because of their inertia. And if the negatives are free to move, we're going to get this, right? We can measure the potential difference. And of course, which one do we get? We get this one, right?